Our final two speakers, and we'll start off with Peter Yates, VK7YP. PY. Oh, of course it is. Peter joined the AOD in 1982, wintered a number of times as electronic engineering cosmic ray research. And continued working as a design engineer in the science labs at Kingston. 1988, he joined the AOD engineering section as the telecommunications engineer and managed the development of the AOD Antarctic communication system until his retirement at the end of 2014. Now, our second speaker, Kim, and I'll introduce Kim now. Kim also trained a bit like Rex, Bureau of Meteorology. Came across to Tassie and went to Cape Grim. My condolences. As part of the WMO Global Program, the Bureau actually saw him involved with Antarctic meteorology programs and participated in, he says here, about 8, maybe 10 voyages. More recently, Kim has come across to the comms area in the AOD and has been involved in a whole bunch of projects like getting NBN to Macquarie Island. So antenna mask rehab programs, the C-band satellite at Wilkins Aerodrome, and support for the million-year ice core drilling. So Peter and Kim's presentation covers a bit of a review of communications from the sort of 1960s through to the present day, and all about the challenges of providing communications in that sort of environment. So welcome Peter, and welcome Kim.
Okay, thanks Justin for the introduction. The Thinking of Cosmic Ray program there, and Andrew showed the picture of the observatory there at Mawson and the tunnel or vault underneath the observatory. And just thinking back, that was interesting. That was built by a miner they employed for a year in Mawson, and he dug that complete vault and tunnel by himself during the year. I mean, obviously with the use of explosives and things like that, but quite an achievement to do that. And the cosmic ray, some of the instruments are located in that vault today, but on the other side, another little vault there is where the seismic instruments are located, since that question on the seismic instruments. Okay, yeah, well, I'm going to sort of give a bit of an overview of communications and the development of the equipment over the years. Tiny bit of history, jumping back to where Ellie talked about the establishment of the relay station on Macquarie Island in 1912, and that used a rotary arc transmitter at that stage. Macquarie Island was then re-established in about 1948 with another 500 watt CW transmitter to send weather and other messages from Macquarie Island back to Australia. That's just a picture that I've had for some time. A lot of my pictures have come from both myself and other radio technicians who have been in Antarctica and send pictures back to the comms group, and we put them in a big store of images that we use as needed for doing presentations and also referring to equipment when we have questions asked on it by our technical officers in Antarctica. So that's the remains, or another picture of the remains of the Mawson's mast at Macquarie Island on Wireless Hill. That's a picture, a much more modern picture of Wireless Hill with the mast there, and there's a number of antennas located on that mast these days, not necessarily shown in that image. It has a repeater located there, and also a number of Yagis for down island communications to link to other repeaters down the island. That's just inside that little hut there, where you can see there's an HF radio as well as a repeater, the MX921 is there. So following on from Macquarie Island, Mawson was established in 1954, again with a 500 watt CW transmitter. That sort of gradually progressed over the next few years with the introduction of radio telex transmissions from Mawson. This, of course, increased the throughput and efficiency of messages. And as there was a gradual increase in the amount of traffic required as scientific instrumentation was introduced into the station, and of course private traffic as well. Then during the 70s, the 10 kilowatt transmitters were installed into the stations. And then along with that enabled the introduction of voice communications, and rad phones were introduced at Davis and Mawson. That's a picture of the 10 kilowatt Collins transmitters there in the transmit building at Mawson. And in between those two sort of black transmitters, that's the NDB transmitter, which I don't think exists anymore there, but the NDB was used for both ships and aircraft for direction finding. That's a picture of the operating desk as it was in, I guess, the early 80s at Mawson, and where we did rad phones from. I remember sitting there and trying to do telephone calls back to family and friends, and sometimes you get a great connection, other times you get basically nothing, and of course that's the vagaries of HF radio propagation. I guess the final main sort of upgrade to the main long-distance HF communications with the Antarctica Division was the introduction of the 50-board telex circuit between Casey and Sydney. This was a leased line, effectively, and it was a full-time telex link with using the Tor system, which guaranteed reasonably error-free transmission. And then Casey acted as a relay station for Davis and Mawson. We've seen several maps, I think, now of showing the stations in Antarctica, but along that red line there you can see Mawson, Davis and Casey, all almost in a direct line with Sydney, where the other end of the terminal was for the 50-board telex operation. And so when you visit Mawson, Davis and Casey and you originally see the big antennas, the big rhombics particularly, that were used to provide the service for that, they're all pointing in the same direction. And the fact Mawson can use its rhombics antennas to talk to Mawson and, Davis and Casey, because it's all in the same line for that direction of the communications. Interestingly, all the Australian stations actually acted as relay stations for some of the other international stations for transmitting the 3-hourly Bureau of Met observations back, which was then from Sydney fed into the World Telecommunication System. That's just a picture of Mawson and the teleprinters in the back room there. And at the time when that was in operation, there was just the clatter of the printers and the teletape machines going all the time in that room. As I've sort of mentioned, to operate these, the long-distance point-to-point HF communications required some quite big antennas at the station, along with the relevant sort of maintenance issues of maintaining these structures in Antarctica. There you can see, Dave, is a picture of the open wire feeders going to the receive mast, or the main receive mast, which on that was hung, I think, was 5 sloping triangle antennas, and they were spaced around the mast to provide the different directions of communications. And that's just look up to the top of the mast there, and you can see the 5 triangle antennas attached there. All the stations had these log periodic arrays. I think at each of the stations there's actually 2 of these arrays, hung off a 150-foot tower, and the arrays are spaced around the tower 120 degrees. So there are 3 of these arrays on each tower, and there were 2 of these towers. Again, a vast sort of maintenance nightmare for the techs at the station. And then, of course, there was more of the omnidirectional low-angle radiation, long-range conical monopole at each of the stations. Around the base of the mast there is a big arrangement of radial wire to provide an earth mat of which the monopole acted against. At Mawson, and this is really just an example of the stations, but those point-to-point HF communications required good separation, or as much as separation as possible, between the transmit and receive antennas. So at Mawson, it had relatively limited real estate available to it. On the island at the top of the picture there, and back onto the other rock, that's where a lot of the transmit antennas were located, and they actually spanned that gap of water, which was fine during the winter when there was sea ice there, and so the water was frozen, and that was good. But during the short period over late summer, when that was probably actual water or sea, if you got a strong wind or a blizzard blowing, you'd get a lot of salt spray and water being thrown up from that and attaching itself to all the antennas. And so you'd get this sort of thing that Tex would find of the masts and wires just covered with frozen seawater. And of course, the weight of that would break some of the wires and the antennas, which would be another nightmare for the Tex to repair. So I think we've probably already mentioned a number of the problems that HF radio has, and this is particularly relating to the long-distance point-to-point communication between Antarctica and Australia. The unreliable propagation due to the solar influence on the ionosphere, which in its extreme led to polar cap absorptions and actually no communications at all. Of course, interference from other radio stations. There was, with all the stations around Antarctica all trying to use similar frequencies, that often caused quite a bit of interference. The limited carrying capability, 50 baud telex, that type of thing. I know that, again, that's changed a lot in recent years with much more digital technology available, but the demand for document transmission, and of course expeditioners had a much higher expectation of what the communication system could provide at that stage. And then I think Rex mentioned the final sort of thing that stopped the point-to-point communications operating was the fact that the Sydney terminal run by OTC, the Overseas Telecommunications Commission at the time, they wanted to close that station. And in fact, I think the Antarctic stations were sort of the last service that was operated by OTC. So again, as Rex mentioned, the division turned to looking to what else can be done and looking at satellite communications. At that stage, and this is sort of the early 80s, 1980s, should I say, very little was known about the practical application of satellite communications in Antarctica. Theory certainly indicated that it would be possible to provide coverage of the coastal stations from a geostationary satellite, and I will show you a map of that in just a second. But there are lots of questions, such as the propagation unknowns. What were the scintillation effects at low look angles of the radio waves pass through the ionosphere, and the variation in electron density in the ionosphere would cause rapid fluctuations in phase and amplitude on the signals. Also, what were the effects of temperature and wind and snow on the antennas and the other mechanical components of the Earth station? There's a map that happens to be of the early Inmarsat system, but there you can see the global beams covered by the geostationary satellites, and of course Mawson-Davis and Casey just fit right onto the edge of those global beams. So it was decided to do a trial in Antarctica using the Inmarsat-A system, one of the first Inmarsat system. These were installed at Mawson in 1984, and this particular picture at Davis in 1985. And they were used to sort of trial satellite communications. This proved successful, but the Inmarsat-A system itself wasn't the way to go to provide a satellite system, partly because of the high operating costs. It only, at that stage, offered manual call connections, and of course very limited data ability as well. So again, as Rex sort of indicated, there was a tender engineering consultancy put out to determine what might be a suitable satellite system. Yes, it was talked about for a while. It's my understanding that the OSAT satellite might be used, which could provide communications to Casey and Macquarie Island. But again, as Rex indicated, luckily we went for, at that stage, to use Intelsat satellites. And I'll show you a map of that in a second, but the first station was installed in early 1987 at Davis, and then Mawson and Casey followed a year later, and then Macquarie Island a year after that. This is a picture of the dome being installed at Mawson. So this was the first private Antarctic satellite network that was installed. At the time, it cost roughly $5 million to install, and we used a team of 8 ATC engineers, technicians and riggers who went to each station and did the installation work. I was actually there at the time. This is my picture of the dome being assembled, and of course they had to wait for a really good weather period there to have about 5 to 10 days to put the dome structure together, because they just couldn't have any real wind during critical parts of the assembly of that dome. So the dome is 12 metres in diameter, and inside that is a 7.3 metre diameter dish. It can withstand wind speeds about 90 metres per second, roughly 325 kilometres per hour. That's a picture of the dish inside, and there you can probably see or work out that it's pointing very close to the horizon to be able to see the satellites over the equator. As I mentioned, the initial system was set up using 2 Intelsat satellites, one over the Indian Ocean, which handled Mawson, Davis and Casey, and then one over the Pacific to handle Macquarie Island. They both fed back into Earth stations at Perth and Sydney, and then over links down to Tasmania. So the very initial ANARISAT system that was installed consisted of 2 analogue Intelsat Vista circuits. One of those was used as a voice circuit, and the other one was used with a 4800 baud modem on it to provide very limited data service. Over time, this system was gradually upgraded with new equipment and extra bandwidth. One of the upgrades, which was about the mid-2005, combined all those different circuits together into one larger data circuit. Initially, I think it was about 384 kilobits per second. This is using the Intelsat IBS service. And technology had advanced enough that we could use this one data stream to provide all the communications to the stations. So over that service, and basically this is an IP-based system where you could pass approximately 8 voice channels, and then when those voice channels weren't being used, the whole bandwidth could be used for data transmission. But one of the things that enabled us to do at that stage was introduce very limited video conferencing to the stations. And another thing we had to look at the time to enable reasonable use of the satellite or limited bandwidth that was provided was use of some form of data compression. So if we didn't have some data compression going, on the left-hand side, they're all sort of all the users' large requirement to transmit data, but when it hit the satellite circuit, you just get very small amount going through. So if we put some data compression at each end of the circuit, then we're able to get a much larger throughput through the system. One of the things we quickly learned with the satellite system and using data compression, that we had to really prioritise the passage of the voice packets. Because they were so time sensitive, they had to sort of be prioritised through the system ahead of any other data traffic. With our initial testing of this, as I say, this is sort of the 2005, that type of time, the technology, a lot of the compressing equipment didn't know how to handle voice. And we learnt this by trial and error, that and in the end, it came down to, at the time, only the Cisco equipment could really handle the voice traffic properly across the satellite system. That's changed a lot, of course, now, but originally we had to use the Cisco equipment for that. Of course, today, the RSO system actually, again, it's increased roughly. I think Kim worked out it's sort of doubled in capacity every couple of years, and so we're now actually, I think, up to about 9 megabits per second to the stations. A number of features then led on from having the satellite communications at the stations. Of course, one of the first things we did in the early 90s, 92, 93, we put in an optical fibre network to all the stations. So this is a picture of Mawson, top part of the picture there. You can see the various coloured buildings, the main buildings on the station, and then the map shows you the cable tray system that ran between all these buildings, on which then the fibre cables were laid to provide the network system at the station. This, of course, then led on to fairly standard pictures you'd see of switches and things in racks, and then all the UTP cabling going out to the points around the buildings. In the back of the rack there, you can see the fibre cable coming in to service then the switches in that rack. Once we started to have good network communications around the stations, we could then do things such as this building management and control system, which had sensors and control units in many of the buildings around the station, which enable us to monitor temperatures and flow rates, and then this could all be monitored actually back in Australia via the satellite system. That's just a sort of a map of the station with the various buildings shown on there, and showing temperatures and flow rates in buildings of both air and the heating hot water. That's just the ventilation system in one of the buildings, where you can see the heating hot water coming in with the blue arrows, and then the air handling ducts with, again, temperature monitoring. I mentioned, of course, that we had, again, the data system enabled us to introduce a full voice system at the stations, so the voice over IP. We based this at the time on the Asterisk voice switch, which we found a very scalable and a flexible solution. It interfaced into all the Cisco phones that were deployed to the buildings. It offered sort of voicemail system, directory services on the phones. It was very simple moves, adds and changes as requirements changed for extensions. And we introduced a new call accounting system so that the expeditioners could have a look at the calls that they made just on the web interface, and that was available full-time to them. Of course, the Asterisk system was interfaced to as well as obviously to the main satellite system, to things like Iridium and Inmarsat as the backup communication. So from the phone, you could access the Inmarsat or Iridium phone if need be as well. Another system that we're able to introduce with the network around the station was, there you can see Mawson, and then there's Base Bay Island and also Werner Island. On these two islands, which are very roughly 3 kilometres out from Mawson, across Kister Strait there, we had penguin monitoring station installed. So on Base Bay Island, there's a daily penguin rookery, and over a number of years, scientists have monitored the birds there. We used wireless IP bridges to do those communications. So here at Mawson, on the transmit building, there's a omnidirectional Wi-Fi type of antenna installed there. omnidirectional because it served a number of links. So as an example, when the ships were in Mawson Harbour there, that's the Iceberg and the Aurora in there together, they both had antennas installed on them that would enable them to link up with the system at the station and provide both email and limited voice service to expeditious on board the vessels when they were at the stations. You can see right out in the background there is actually Bay Island. And so on Bay Island we had these huts installed that provided living conditions for the scientists who were working there over the summer. And that's the link, the other end of the link on Bay Island with the directional antenna pointing back to Mawson. And then down in the rookery, you can see there the Penguin Way Bridge, where all the penguins have to walk out over. They pass over that as they're going out to feed, and then when they come back, they're weighed both when they go out and when they go back. They have little tags on them to identify the birds, and so a large database is built up over time of looking at the feeding habits of the penguins on Bay Island. Of course, as Andrew, I think, has mentioned, quite a few other scientific experiments are run at the stations, all because there's this good satellite communications system to get the data back to Hobart and to the other operating centres. Andrew's been through some of it, but there's geomagnetic observations for GA and seismic observations, ionosondes, Cosray Mawson, tide gauge program, and Panza UV monitoring system. As I mentioned before, this is at each of the station, the transmit and receive facilities are well spread apart to provide diversity. That has changed. We don't need such separate receive and transmit areas now, and so you actually find there are transceivers probably installed both in the transmit and receive buildings these days. That's the HF receiver building at Casey. So there's obviously a VHF unit in there as well. Open wire feeders to the antennas. That's a sort of older picture, but separate receivers there as well as a codone transceiver. The Casey transmit building, which I've got a picture of in a moment, and as we've seen a few times, the Davis operation building and the NRSF dome. And then equipment in the Davis operation building there. I'm leading up to just showing the operators' consoles that have been installed in the buildings and then developed over time. This is sort of one of the earlier ones that use Zetron system, with the mechanical switches there that switch the various radios onto the operator mic and speakers. It's more recently been replaced by IP system. This one that Warren sent me through a picture of the other day, there's a new system installed at Casey. It's based on a Zetron fully IP operational system. So that's the interface gateway that the radio connects into, and then the box puts that onto the Ethernet. That's a picture of the transmit racks in the transmitter building at Casey, which have two Barrett 2050 transceivers in there with 1 kilowatt PAs, and then you can see the two Zetron radio interface units there that connect back to the operator console. And also you can see a couple of the blue MX921 VHF repeaters in there, which I'll have a look at in a moment. So then on the operator console, you can see that the operator can access sort of all the VHF units as well as the HF units from the operator console. And of course, once it's in IP, you can actually operate or connect to these units from anywhere within our LAN system. So an operator at Mawson could actually access a transmitter at Casey if need be. There were a couple of other screens shown in that initial picture. One of them is used for aircraft tracking. So when the plane is flying, say, from Hobart down to Casey, you can see the tracking that on the screen, and also all the helicopters we use have trackers installed on them as well. The other screen there was used with the Garmin, the InReach Mini personal trackers, which are GPS and Iridium tracker. So then the operators can track where the field parties are who have those units with them. And that operates by Iridium SMS messaging. In fact, you can provide short messages over the units to provide messages. It's not a voice communication on those units. Of course, our vehicles, the Hagelin over snow vehicles, have a good set of communications and navigation equipment in them. It's an earlier picture of where they have the Furuno radars installed on them. These are the older sort of 4 kilowatt pulsed units, which are big sort of heavy units and take quite a bit of power to operate. We've more recently upgraded to the Lowrance CW, continuous wave marine radars, which are a lot lighter and a lot less lower power consumption. And then in the vehicle you have a much lighter display that provides both the sort of the radar image when required, and also maps and tracking in the vehicle. You may wonder, in fact, I probably should say, why do we have radar in a vehicle? So these vehicles will travel away from the station, either on the sea ice or, in fact, on the plateau. Once you get away from the station, there's very little to identify in terms of navigating, and so the radars are very useful. One for tracking. We have various routes set up with canes on them, and then radar reflectors on the canes. So with the radar, you can follow along a cane, so-called cane line, to get from one point to another. And when you're on the sea ice, particularly my experience at Mawson, when you're on the sea ice and you have a lot of islands and things around, so you can identify, say you're in a boat, you can identify the islands and know where you are and travel along. Of course, GPS has added a lot to that these days with maps and things available, but the radar is extremely useful when you're in your low visibility conditions. If you're in snow or so-called whiteout, then the radar can be a lifesaver at times. And then that's just a picture of up on the plateau going to an automatic weather station inland from one of the stations. I'm not sure which this one is, but both Casey and Mawson have weather stations quite a way inland on the plateau. So I want to a little bit about VHF repeaters. We use repeaters to really extend the coverage of local communications at each of the stations. This one happens to be at Tarbuck Crag at Davis, and you can see it's high up in the hills there overlooking the area, provides a very good coverage around Davis Station. Of course, it's used for things like boating communications, people, field parties, when they're out visiting a local field hut, and of course for aircraft communications. As I mentioned a couple of times now, the MX921 is, I think, the most recent repeaters that we're using. They're actually manufactured in Western Australia by Spectra Engineering, and they're one of the very few repeaters that I could find at the time that provided very low current and low temperature operation. The low current is particularly important to us, sort of low standby current, where over winter, when one of these units are installed, and I'll come back to this, but at a repeater site, over winter we get very little solar radiation, obviously, during winter, and where most of these repeaters initially relied on just the solar input and batteries, we needed extreme low current operation to enable the repeaters to operate throughout the winter. Sorry, that's just a picture. We use these half-height 44-gallon drums, galvanised drums, to house the equipment in. We find it's very robust and weather protected, works very well. And that's on top of Mount Parsons, which is a mountain close to Mawson. There you can see a perspective of Mount Parsons, and in the distance you can see Mawson marked there. Quite a epic trip to be able to get to that repeater. You can drive a vehicle to the hut that is near Fang Peak, and then you have to walk from there and climb up onto Mount Parsons. Unless, of course, in summer and you just might have a helicopter available to you. But if you've got to get there in winter, that's how you have to do it. In more recent years, we trialled wind generators at the sites. This one at Mount Parsons, and also then this one at Tarbuck Crag. That has enabled just to extend the life during winter of the repeater operation, along with the low power repeaters. That's a picture of one of the repeaters at Macquarie Island. I'm not sure whether it is Mount Jeffries that Ellie showed earlier on. There are two sites there, Mount Jeffries and Mount Elder. There at Macquarie Island, we use these small water tanks to provide the protection of the equipment, and it also enables the tech to get inside out of the weather when they need to work on the equipment. More recently, again, we're going through an upgrade program of the repeater sites at Macquarie Island. Again, still using the small water tanks, but we've been able to utilise sort of modern flexible solar panels and actually install them on the side of the water tank, and also trialling some wind generators at Macquarie Island as well. Another one of the projects obviously involved communications has been the Wilkins runway near Casey. So Wilkins is located roughly 60 kilometres sort of south of Casey, at round about 700 metres up on the plateau. There you can see Casey Station, and then Browning Peninsula just south of Casey there. When you have a look at the path profile of Wilkins runway site, you'll see either from Casey and Browning Peninsula, which is slightly better, there's still the large bulge of the ice plateau that gets in the way of any direct communications between, say, Casey and the runway site. We did some trials at Browning Peninsula there to see if we could get any sort of reasonable communication through, but we just couldn't. And that's the repeater site at Browning Peninsula. It will still provide quite good communications most of the way of vehicles travelling up to the runway, but it can't quite reach the runway itself. There's very large infrastructure installed at the runway. This is a sort of an early picture of some of the early infrastructure there, all based on basically containers installed on sleds. And the green building there is what was the communications office at the time. I should say on top of that you can see the Inmarsat BGAN antenna that provides the service back to Casey for telephone and data. That's progressed on to more recently they've put in larger buildings and tried to reduce from multiple lots of little containers into just one or a few big ones. That's sort of one of the living type buildings that they've now built. Just back to the little communications building, and in there, fairly originally just put together at the station of Inmarsat, Iridium Communications, and there's little HF there and VHF Communications. Then the new communications and operations building being put together for Casey. The sort of double height containers there on that mid-height is actually a sort of deck or balcony that enables the operator to have a look outside and overlook the runway and the operations that are happening. And then the top deck is used for the antennas installations. That's it actually in operation, and you can see the antennas on the top deck there again, the Inmarsat BGAN antenna along with other VHF antennas. That's inside the top building there, overlooking the runway sort of area. And then a rack of equipment to provide the communications. One of the interesting things is we, between each of those main buildings on the runway, again, we've provided IP Wi-Fi type of communication, which then enables IP phones to be put out into the buildings, and there's a little asterisk voice switch again here in the rack that provides local phone system to the runway, and then it's interfaced into both the Inmarsat and Iridium satellite phones to provide communications off or away from the Wilkins runway. Again, pictures of the antennas on the top deck. We did trial an HF system there. There's an NVIS, near vertical incident antenna there from Moonraker. The loop sort of antenna that's there. I must admit I'm not across how that worked at all, or whether they use that for HF communications or not, but it was an antenna we were going to trial because we wanted sort of the sleds needed to be mobile and be able to be moved around, but therefore we couldn't put up sort of big any wire antennas, and this was just one option we were trialling for that. That's the Inmarsat BGAN with its dome removed, and in there you can see the little coil that we had to put in to provide a very small amount of heating into that dome, because when you look at the specs of many of the sort of Inmarsat and Iridium type satellite communicators, they only work down to maybe about 20 degrees, minus 20 degrees C. And of course, Wilkins will experience temperatures lower than that. And so we needed to provide a small amount of heating into the dome. Another project we've been involved in is sort of communications for some of the field camps that have been set up over time. This one is of Heard Island, and I think this is actually it's Spit Point on Heard Island, not where the main station was originally located. You can see all the sort of living tents there, and then the water tanks that again used as living area and communications. That's a picture of the communication hut, and in that orange container outside of the hut is actually an Inmarsat B flat panel antenna pointed towards the satellite. Inside again, a couple of little racks of equipment with both HF, VHF and the Inmarsat terminal there. And then on the laptops, we actually ran a small email system of a store and forward type of email system that people could have their own accounts on the laptop, or also link in via Wi-Fi into the laptops and access the email server that's located on them, send and receive their emails. Then when there's enough emails stored on those systems, it'll connect through the Inmarsat terminal and transfer the email back to Australia and vice versa. Of course, solar panel to provide power to it. Up behind that, there's a VHF mast or antenna installed and a small wind generator. Also, away from that main sort of base camp, there were a number of other little camps installed, some that had a water tank installed, on which you can see an HF antenna, VHF and Iridium antenna there. And of course, then a power system of a small wind generator, solar panel and battery. their similar system providing a group of small tents. Very similar system I use on some of the inland glaciological camps. Again, using Iridium to provide the satellite communications and VHF for local communications. Before they departed, we set up these containers housing the equipment and doing some testing on it. There are all the antenna cables prepared, ready to go. See, there's QMAC HF radio there, an Iridium portable phone, and VHF unit for, in fact, that's probably an air-ground unit for aircraft. Then when it's in that tent, actually in operation, providing the email and other communications. And I think that's it from me. So thank you for that. And we can have some questions if need be, and or Kim may want to show some pictures.
You talked about the system providing you with the IP-based system providing you, and the greater bandwidth that the satellite system provided you with, a whole lot of opportunities. I assume you were talking about Kingston monitoring and potentially controlling things on those bases.
Yes.
Was there a network operations centre set up at Kingston where all of that sort of came into and was consolidated?
Yep. There was. I must admit, this is where, since I haven't really been involved since 2014, I'm not sure what it's progressed to now, but certainly at the time we had a whole wall of displays mounted there, which were providing network monitoring, providing satellite monitoring, and of all the equipment in the satellite terminal at each of the stations, we can monitor all of the equipment. And then all the sort of full network monitoring, such as all the switches and routers and things at each of the stations, we could monitor them totally from Kingston. And there are probably other things too that I'm sort of missing, but yes, definitely a big monitoring system there at Kingston.
And alarms would be.
Yes, that's right.
Okay, cool. Thank you.
Yeah.
One of the earlier slides you showed the 7.2 metre dish inside those lovely domes.
Yep.
It strikes me that's a very fine beam to point at a geostationary satellite, which are not really stationary, they do wobble a bit. Do they have to be tracked at all?
Yep. So they all had trackers installed on them initially. We had various success or not success with the tracking, and in fact the early equipment that was installed, it just didn't work very well and failed. We then found that, in fact, while you're right in indicating that the 7.5 metre or 7.3 metre dishes had a reasonably fine beam, it was wide enough that the movement of the satellite within that beam, it didn't require much adjustment. It was sort of very little adjustment was required to keep the system operating. It'd be different if you had a much larger antenna there, but we found that you could operate successfully without the tracking operating on the antenna. That has since we've put in newer tracking system to it. So the antennas, I think, do now actually operate with tracking on them, but we did find it wasn't absolutely necessary to have it going.
Can I add a bit to that, please, Peter?
Yep.
The tracking systems that were in the later version, they had a particular type of memory that only wrote to the same location every time, and they've all systematically failed and we can't buy replacements. And so as part of the upgrade, we're going to replace the tracking system, but the tracking's actually turned off at all the stations, and the beam is wide enough that the satellite stays inside its orbital box and everybody's happy. So it's quite remarkable that over that period of time. They just stay there, which is fantastic. Thanks.
Peter, was it just fortuitous that Intelsat included high latitudes in their business plan from the start, or did we have some influence in that? Or because there's not much of Antarctica that is really accessible for Intelsat. So yeah, what happened there?
If you can't get Intelsat coverage,
Well, I'm just thinking, like satellite users these days have very targeted beams.
Yes.
And like Intelsat seems to have covered, all of the high latitude regions.
So they're doing that, or we're doing that through them with what we call global beams. So it's just one beam,
right,
illuminating the whole of the globe from what the satellite can see. Of course, Intelsat then have lots of other smaller beams to illuminate particular areas. But as far as I'm aware, they don't have any or very few of those sort of beams really pointing at Antarctica itself.
Right.
So we're very much reliant on the global beams. Some of the Intelsat satellites have half hemisphere type beams that we possibly can use a bit, but again, they're aimed at the high population density sort of areas. Interesting. We've mentioned Inmarsat a number of times, and Inmarsat have had quite a lot of development over time through their satellites, and they've now got, certainly fleet broadband, but maybe another generation on, where they've got their coverage of the globe is done with a whole lot of small beams. Right. And the issue we found with them as they've moved into that area, again, it's population based, and so they haven't actually even turned on the beams that cover Antarctica because they just don't have enough usage of those beams. And in fact, the satellites don't actually have enough power to illuminate all the beams at once, so they have to choose which beams they illuminate. And yeah, again, it's just aimed at population density. So again, even with Inmarsat, while they have that sort of much higher throughput capability, we still have to rely on the more global beams with much lower data capacity to cover Antarctica.
Yep. Thanks.
Cool. We might, no further questions. We might change over to Kim.
I knew that Peter would do an exceptionally good job, so I could slack off a bit. And so what I did was I just went through and took a heap of photographs off my endless supply of photographs, and some from the system and some from... We run share files at work, so whenever people are doing things, you always tell them to take photographs so that when somebody flies on a year or 2 or 3 years later, you know what was there and what wasn't there. So I've got some of those photographs. But just coming back to the referencing to the satellite system, our service provider now, Speedcast, and they're an Australian company based in Mawson Lakes in South Australia. The throughput of the satellite systems we've been using, like the RST-100, there was one sitting in one of the boxes in Heard Island. They were 9.6K, so that's really rocketing along. The BGANs are 340K up and down. We're using Certus Iridium's base system now for some of the ships, and they're 352 up and 704 down, but they're talking about going to a meg soon. So the Inmarsat started off, as Pete said, at 380K. The next increment was 500K in 2010. Then we'll just jump through. By 2014, it was 3 megs, and now we're on 9 megs. And that's both ways simultaneously. And Tom and I had the discussion on Thursday about whether it was 9 megs one way or 9 megs both ways. And he was going, I said, I thought it was one way. And he said, yeah, I think it's one way too. But we actually brought the monitors up on the computer and had a look at it. And you can see the surge in the data throughput from the station. And there's a point where both are at 9 megs. And so that's done with carrier, and it's black art type stuff where the modems, the Newstech modems, are listening to what's being transmitted, and they take that away from what they're receiving, therefore they know what they're receiving. So it's done on the fly, and then you've got things like extender boxes which control the surge of data, and they'll prioritise the traffic so it goes through. It's really quite neat. But then I also got told from Andy yesterday, who was at Casey last season, he thinks there's actually surge capability between the stations. Through the Speedcast system, and I haven't confirmed that yet, but if that's the case as well, it's just amazing the amount of computing power that's running behind the system to maintain those comms.
Yeah, the surge capability is an option, if you move that way, it's with a slightly different system on their satellites, which my understanding is we don't
have it yet.
but
Okay.
it's certainly a capability that is possible to introduce there.
Good. Wilkins is running BGAN at the moment, so it's 340K, but we're looking at putting in a 2 meg satellite system there. And what we're tending to do now for ease of installation is to go to the marine type systems where they come with their own radome. And that's what will go to Wilkins, and we're sitting on top of one of the containers. You need a heading for it because it has no reference for itself. So that's accepts the NEMA string, so we'll put a HS60. The original, there's another complication with navigation in Antarctica that we haven't alluded to, but because the tilt angle is so high on the local location of the magnetic pole, because up here all of the force lines are basically horizontal, but as you come down to the pole, they all tilt down to the pole. And so your horizontal component on your magnetic compass is quite short, and the compass is very sluggish. And so you can do a 360 and nothing very much happens. So now we're using HS60s, which are a short baseline GPS compass. And so they've got 2 receivers in them about 50 or 60 mil apart, and that'll give you your heading, because the other point compasses we're using didn't work when you're stationary. These actually will give you your heading when you're stationary, and that's what we'll use on the satellite system, so it knows which way it's pointing. So that sort of covers that. Noyena's 4 megs peak. You remember that? 4 megs?
I think that's what it's
4 megs.
is going
Yeah,
to
thanks,
be,
Bert.
but again, I haven't seen just the latest
Yeah.
what it was.
And it was split up into 4 1 meg silos, which will probably get rearranged because that doesn't allow sharing between the silos, so that'll have it in the near future. And one of my projects, which I'll show you a photo of in a minute, was NBN for Macquarie Island. When NBN was instigated originally, one of the specs was it covered all of the Australian continent, Tasmania, and the offshore islands. And you sort of go, yeah, okay, so you go Norfolk, Lord Howe, Cocos Keeling, Christmas, and the last one is Macquarie Island. So we went, oh, this is pretty neat. So we looked around and we got the terminals from Macquarie Island, for Macquarie Island. They're just little 1 metre dishes now to put them in a housing because they wouldn't last 10 minutes down there. I found some marine radomes that Sailor use for their small systems. Brought those in from Europe. They were ridiculously expensive. Put them on a stainless steel stand and off we went from there. Now, if I go mouse to, oh yeah, you're right about the slow mouse. Go there. Yeah, now we're right. Okay, here we go. Yep, we have it. Okay, so stainless steel stand, the bottom section of the radome, which is the base, and you've got to think marine for this. If you look at the array, yeah, it wouldn't last very long. It's all steel and aluminium. So page down, shift down. Right, clear, that one? Yep, there we go. Now the base is stainless steel. Those 4 things sitting next to them are called shorefoots. And if you ever are in an amateur situation where you want to put up some sort of mast, they're relatively cheap for complete systems, $200 or $300. But what they are is really heavy-duty galvanised plates, and then you drive hollow tubes down through them, and they go down about 1,200 mil. And so there's 2 systems sitting at Macquarie Island. They've been in now 4 or 5 years. They haven't moved. They're absolutely fantastic, and they're portable. So you set up a search and rescue exercise, and everybody carries it up to the top of the hill, and then the riggers put them in. So fantastic system. So right click. Ding, ding, ding. Come back. Chasing this mouse around. Oh, it's not, isn't it? Can we use this one? Yeah. Right click there. Yep, there we go. And there it is. It's assembled with the radome on. Lug in the top so we can lift it on and off with a fork. Just purely assemble and handles all, just marine handles all the way around, so you can lift it up and slide it down. Now, in the middle of it, you can see the Anarisat dome. The little dot just to the left is the dome for NBN. Now, when NBN went in, we had 5 megs up and 25 megs down. But the problem was we only had a relatively small data component because it's set up for households. And it took something like 18 months to find a service provider that would give us enough capacity that we could run it on the station at a viable level. And because it was a relatively high-speed link, and with the demands on data now, like phone updates, computer updates and everything else, that was what it was primarily used for, and it still is, I think, fundamentally. It's not used as an operational like an RESAT type component. But having the second one up on top of Wireless Hill gives us the ability to combine the two together. And there it is there. So that's the top of Wireless Hill, a few years on from Peter's photograph. The climate's still the same. The geography's still the same, but there's a bit more stuff there.
Yep.
Yeah. And so that one sat there quite happily on shorefoots now. I'll probably put the mockers on it, it'll blow over next week, for some years. An amazing product and very durable. So here, I'm quite happy with it. Okay, escape. Can we go back? No? How do we go back?
I think we're meant to be able to access the NBN business system at some point, which will provide much more data capacity.
We're onto a better system now, but okay, thanks. I have no idea what it is.
Yeah.
Okay, we don't need to worry about that. Let's go to AA, Australis. Now, I did a few years in marine science, so, bing. Okay, this is the bridge on Australis, and that was the main comms console, scanty equipment that was made redundant by the progress with satellite comms, and it's no longer there. This is in the actual, was the communications room effectively. Now it's the First Mate's office. So that's all gone. The NDB's still on board. So we're into dry dock. I went to, the ship had to go to Sembawang for an extension of life project. And so we got flown up to Singapore. And this is sitting in the dry dock. That's the bottom of Australis. Dry docks in Sydney are really easy because they're all Australians who set the ship up. So the ship's at about this height, so it's really easy to work. The guys in Singapore are shorter than us. So we were sort of halfway between kneeling and crouching the whole time. And it was not fun. And it was hot. So there she is sitting in. She's been sandblasted off and the undercoat paint's going on. And looking down. So for access into ships when you're in for a while, we flew up, pulled our transducers out, did the things we had to do, then came home for a month or something and went back up. So there's no problems with cutting holes in ships to get access when you're in for that period of time. And the work crew on board was, must have been 100 people. Sembawang's the old British dockyard. Yeah, and they are amazingly well set up. The ship was out in a floating dry dock, right at the end of the wharf, and it was 3 kilometres away from where you go through the main gates. And this is the Malacca Straits behind the dockyard, because we face into the dockyard. And this was the level of traffic going backwards and forwards. And the crew on Australis were saying when they went in, the pilot came on board and he was timing their position every 30 seconds. It was that critical. They had to start at a particular time and they had to be through. It was just like going down a freeway, but more orderly. And under the ship, there's the guys working under the ship, and she's sitting on these big blocks, and that bloke's doing a touch of sandblasting. They said to us, oh, it's going to be noisy soon. They're going to do some sandblasting. You've got your earmuffs, you'll be right. This is only a trial. We're going to blast the rest of the hull at night. So there you go. It's a bit blurry. Test patch number 2, 1,000 bar. Right? 1 square metre, 25 minutes. They didn't like that. They thought that was a bit slow. So we go to the next one. 1,000 bar, 4 minutes. And so they changed their grit compound or their nozzle shape, and that's it. And that was it. And that's how they did the hull. It's just unbelievable. But you wouldn't have wanted to be within hundreds of metres. Even with full earmuffs and things on, it was pretty appalling. Yeah, 1,000 bars. So what's that, 14,000 PSI? 14 bars, 14 PSI? Yeah, 1 atmosphere. Yeah. Okay, so when I was doing marine science, I'd sold my business off and I was looking for something to do, and they advertised for a marine science guy, and I went, yeah, I can do that. I've done one voyage with. I find it amazing there was 3 of us here that were involved with the sad days of Neladan, the end of Neladan. And so I sort of applied and I got a job, which amazed me. So I'd been out of electronics for 15 years or so, or formally working it. So Tony Vaness was putting together this project on behalf of Martin Riddle, and it was a census of living life in Antarctica, but it was predominantly below the surface. And so we needed a camera system that would allow us to traverse the seabed and take photographs. And CSIRO had developed a system they were using on their ships, and we sort of jumped off that. So this housing is good for multiple thousand metres of water, and it's stainless steel, and where you see the Allen screws, the front goes in with a couple of O-rings, and as the pressure goes on, it seals. It's fantastic. And the strobe in there is a Canon strobe, off-the-shelf camera strobe, and we were banging them every 30 seconds for hours. Eventually, that one has oil in it because you can see where the oil level is. That was supposed to improve it. It actually made it worse because we found we had degradation because of the oil. So it's a pretty amazing application for something which is quite an off-the-shelf item. The cameras were 7Ds or something, the standard Canon digital camera, and they took thousands of photographs. So the longest run we did was one drag, which we started in 100 metres and went out to 2,000 metres of water every 30 seconds, and it would have been getting dragged at a knot. So yeah, there's hundreds and hundreds of photographs. So this thing is called a beam trawl. And when you look at it, on the right-hand side there's some instrumentation that gives us the depth, and also it's a small CTD, so it's a small conductivity, temperature and depth instrument in that orange housing. The camera's in the middle there in the housing. There's some better ones than that, better images than that, but that's in the middle, so it's looking down. It's looking at the ground or the seabed in front of the beam trawl, maybe 5 metres, and the net is just a drogue to keep it stable, and there's a depth sounder on the left-hand side as well. So now you can see it. The camera's in the middle with again, same concept. It's an aluminium housing. It was rated to 3,000 metres, I think, from memory, 2,500 metres. And the front screws in, the camera just sits inside in the cradle, it's held there. There's strobes on the left-hand side and strobes on the right-hand side. You can see the strobe in that stainless steel housing. It's in that position because it hasn't been turned around to go to sea yet. So all of the gear is rated for that sort of depth of water. All the cabling is rated for that depth, and it just works impeccably. Gold connectors with rubber bases around the connector, and it pushes into a socket. As the pressure comes on the outer rubber, it just squeezes it down, and it locks up, and they will never leak. Assembled properly, they're fantastic. Some of those connectors are rated for thousands and thousands of metres of water. And that's the sort of image you pull up. So that's the bottom in probably 1,500, 2,000 metres. So it's quite barren, but all of these creatures that look like they're actually flowers or critters, they're actually live animals because there's no photosynthesis down there, it's too deep. And so the topography can be quite flat, or it can be all over the place, up and down, where there's been, if you're in the shallower water, say maybe 500 metres, you'll get scours from the bases of icebergs, and you'll be looking at your images and all of a sudden the beam trawl just falls off the bottom and drops down 100 metres or so, sometimes with catastrophic effect. And as you come back up, that's what Australis' rudder and propeller look like. And that's what a bit of ice looks like underneath. And there's the rear view of the beam trawl. The green mat was an anti-wear mat, and the actual trawl itself's that net. Now, as we progress through, there's a front image, that's using LED lights because it was a video trawl. We ran video as well, a Canon video network quite nicely. And that's the sort of thing you drag up. Those sponges are actually glass. And so the animal that makes them goes backwards and forwards along the individual strands and accretes out of the seawater silicon. And so they're glass sponges, and they're actually quite prickly. And they were about, as you can see from the guy, they're about 500 long. And there's samples off to the other side of the ship there that have come out of the beam trawl. So fish, I'll click through reasonably quickly. The wet lab, everybody gets a job who's involved with the science program. So this involved multinationals. There were a French team, Americans and other people from all around the world. And how they run these operations is that a principal scientist will come up with a concept, and then they'll sell it for funding so they get ship time, and they franchise out all the science around the world, and you'll get people coming in who want to do it. So we're back to, there's the connectors. So gold connector and the rubber base, and the two come together, so it's male and female, a little bit of silicon oil or silicon grease around the rubber base, but not enough to actually hold it apart. And it just slides on really nicely. And as the pressure from the outside in the ocean comes on, they just tighten up and tighten up. CTD for collecting water samples. the side door of the ship opens and goes out on a gantry and lowers down. There was about 5,000 metres of cable on board, and it's hung off a non-lifting cable, which is 6 millimetres in diameter, with 2 conductors inside. And if you look at the tops, just under the top ring, the vertical tubes are called Niskin bottles, and all the lids are cocked. So they go down open, so by the time they get to the bottom, they've been fully flushed. And as you come up, you can remotely fire them. Now, the power and the control signals and the data goes up the single conductor, or the pair of conductors in the middle of this cable. And there it is inside, ready for deployment. It's cocked. And here we have somebody milking it, going around taking the water samples. And so they're the big bottles. There's 20 litres in each bottle, and there'll be various samples taken from each of the bottles into different bottles that are allocated positions in the whole structure of the data set, and then they'll go to different people for analysis on board. And this is just, I was walking past the screen in the workshop one day, I took a photograph of it for my own reference, but it is quite useful. That's the density of the sampling. And so you can see on what is effectively the western side of the chart, the vertical line, that's where we've sampled down, coming down from Antarctica, and then we've moved off to the east. And each one of those points is a sampling point, so you ran 24/7, just going point after point, and the blue object's the Mertz Glacier, where it comes out to sea, which is not there anymore because the tongue fell off a few years ago. And this is the conductor. So the cable's about 6 mil in diameter. The CTD rosette assembly, when it's fully loaded with water and coming out of the water, coming up or recovered to the surface, weighs about a tonne. So that cable both supports it. It's a double layer of steel and the 2 conductors. And so these insulating cribs, they're a heat shrink insulating clip to join the wires is what we use, and you'll join them like that. And the left-hand side is the rubberised cable going off to the instrumentation. And then this is one for another device that's multi-conductor, but same principle. And then they get, you put some heat shrink on first, you shrink the heat shrink down onto the rubberised cable, leave the top end open, and you use a compound, a potting compound. Now that will do, on the multi-core one where it's the RMT, it's not getting used as much, it'll do the full season. On the CTD, you might do 100 drops and it'll still be fine, as long as there's no air voids inside it. If it's fully homogeneous and sealed up really well, there's nowhere for the moisture to come in or for the water to come in, and it works an absolute treat. I was amazed. Now that's a ship you might have recognised, blue and green, the Investigator. She was getting built in the corner of the Sembuang dockyard whilst we were there, literally in a corner. So that was a few years ago now. And the ship alongside had come in for some refits. It was some sort of processing ship. And the aft module, you can see with the crane over the top of it, that aft module filled up the entire road coming in, which was 4 lanes. And they brought it down on a low loader, put it alongside. That floating crane came in. It was an Atlas 1,000-tonne crane came alongside, had it on, welded down, and off they went in the morning. The scale of this place is just astounding. This is one of the labs when you're at sea and working. It looks pretty messy, like there's stuff everywhere, but there's stuff everywhere because there's so many people working. Come on, Andrew, give me his name. I can't remember. I'll think about it in a minute. Did a few voices. Okay, get rid of that. This is the aft control. This looks messy because it is messy. There's no space, and we'd outgrown that by that stage. Polar Queen went to Heard Island on her. Heard Mawson Casey Davis case. Now this is when you're down with transducers in ships, you've got to service them. This is the access down to the bottom of the hull, and that's when you start going along. And I'm not very big, but it's sort of a bit of a squeeze. You see, you keep progressing along, and eventually you come to a point where there's a limber hole in the frames. And so that hole's about that high and that wide, and Tony, who did yoga, could actually get in there and sit on top of it to undo it, whereas I had to go in through the side. So you disconnect the cable, and that's all you're in there for, disconnect the cable, and then the rest of the work's done outside when the ship's in dry dock. So you're 25 mil apart from the thickness of the hull, but there's all this rigmarole involved. And that's the window that's over the transducer. Some transducers are open to sea, so there's no change of characteristic through the actual space where the liquid is, because there's water on both sides. And this is just a plastic that's basically the same density as water, so it doesn't affect anything. Then there's other ones like this one, which is the deep water echo sounder. That'll go down tens of kilometres. And that one has its own window built in. We also have pingers on board to remotely control instrumentation that's sitting on the seabed. And this is one of these pingers. And there's the prop shaft coming out. Again, it's Semboang. And there's the rudder stock. So, you know, ships, everything is big with ships. There's just nothing half-hearted. This is a whale listener. And it's activated by that last echo sound or pinger that you saw. So this is lowered, it goes to the bottom of the ocean, it'll sit there for a year or so. I think they're good for about 18 months. And it records whales. So normally you only drop it into about 1,200 metres of water, and there's particular places I like to put it because they know they're on whale transects. And so it just sits there and records whale sounds. And go back one. In that black vertical tube is a ballast plate, which is a lump of steel that's circular and about that long. So when you come over the top of it and you ping it, and each one has its own ID, and sometimes depending on how the strata of the ocean's going with density and temperatures, you'll have trouble actually activating it, and you might have to muck around for a while before you get a response back from it, and then you go burn. And what it actually does is that link on the top there, you can see the black one with the plastic on it, that's a fusible link. So they put all the battery power into that, and there's one on each side, and they fuse. And as soon as they fuse and go open circuit, the weights drop out the bottom, then it starts heading back to the surface. And depending on how long it is, or how deep the water is, it can take 40 minutes to come back up to the top. If it's flat, you can see it, it's really nice. But if it's a bit choppy, it's hard work to find out where it is because you've got to hold station, but you just hope that the currents underneath you are such that it comes up next to you, but not under the ship. Yes, a few have been lost. And to get the hydrophones away from the bottom, they're actually attached to the top of this string, and the string with the two buoys on it, so you can see it. The buoys are glass spheres because they're durable. Sorry? Okay, there you go. That's it coming out. Bingo. Sometimes you have to build things on board. That was a really quick and dirty wire out counter. There's the other side of it. And this was a ADCP for a lady who was doing a science project, and she didn't have any spare batteries for some unknown reason. They got left behind. So the A factor, if you like. So we went, okay, let's go and have a look at our container. So we went through and found as many 9-volt batteries as we could find, and we had enough to do 2 recharges for it, which made her happy because she actually got her project done. Okay, that's me, done.
Thank you. Any questions for you?
Make them easy.
You mentioned the device that I would call a differential GPS, HS something.
HS60, yes.
How much for that?
About $1,000.
That's pretty good.
It is very good. There's one on top of every hag, and anything else that we need to know it's heading for accurately, like the boats. HS60, it's Simrad, I think, remember? Or it's either Simrad or Lowrance, but the 3 brands are actually produced by the same company. They're just marketed with 3 brands. Yeah, good device. Any others? Yes.
Just a very quick one. Is there any need for low latency satellite comms at the moment?
There's always a need for low latency.
Yeah, and are we going to think about that?
Yes. We've looked at we've looked at a few. How's that? I look at myself. It's in vain, isn't it? We've looked at some of the service providers, but when you look at them, a lot of the polar orbiting satellites have got a really heavily inclined orbit because they're interested in making money, and they don't go where there aren't customers. There is one that has orbits that go straight over the pole, and we will use those in the future. Now, whether you use them for a store and carry type situation, where you're just uploading data and sending data elsewhere and it's coming down through a ground station and back to you, that's a possibility. If you want to do voice, you need more satellites. And Tom and I had the discussion the other day about that because this is one of sort of our ongoing questions. And we were thinking about laser-to-laser transfer between satellites. We sort of came up with a figure of about based on 600 or 700 kilometre above the Earth orbit, we think that you'd probably be able to communicate up to about 4,500 kilometres between satellites. So that's probably the limiting factor. We've had some issues with iridium down south where people have come outside with a handheld and they've got the beacon there, but they can't talk, and then they'll try again the following day and they can't talk, and the third day it's okay, or they seem to come and go. And I could never get to the bottom of it, and I sort of, sometimes you hear things, you only hear them as hearsay and they're not really factual, but I burrowed back through to find the actual people who have done it. And one guy has had a lot of field operations, and he told me that he had it occur in multiple places. We wondered whether it was just one particular area of Antarctica. So we suspect that they power down some of the satellites to conserve power when there are areas where they don't think there's very many customers. And through one of our suppliers, I got back to Airbus in the UK, and one of their engineers was looking at it, and he couldn't come up with a solution as to why it might be happening. But then just in the last few days, I was talking to somebody in the military, and they were talking about different tiers of service from iridium. So, because I could never understand how they can be flying military planes around and using iridium and not having the same problem. It just doesn't go hand in hand. Which brings me back to HF. And some of those photos of yours, Peter, I'd never seen before, so it's good to actually see them. We still run HF. We're running the Barretts with the kilowatt or the Barretts barefoot with 125 watts. We are consolidating because, as Peter stated, in the early days you needed separation because you were running continuously transmitting and receiving. So we're coming back just to one transceive location. Some aircraft use iridium, some aircraft use VHF marine, some aircraft use HF to talk to us. It depends who they are and where they are. But there is a requirement for HF. And HF's a really good fallback. And I've bought some of the Barrett man packs to replace the QMAC HF90s. They're at the stations now, although we haven't actually progressed into using them yet. It's a job for this year. And we're upgrading all of the antenna facilities. We had a multitude of masts across the stations to the point where we couldn't maintain them all. So for the last few years, apart from the COVID period, we've got rid of everything we don't need, and we've got new masts going in. We do want freestanding towers, but that's a massive amount of work. I'll be just about dead before they get done. So we're putting up some temporary masts, which were temporary 10 years maybe. And the other problem we've got in Antarctica with a lot of this stuff, if you go to freestanding towers, you need a massive base to hold them up. You've got to be confident of the geology underneath. It was explained to me by Mark Pekin one day. Mark's one of our engineers. Mark said one of the most difficult things you can make in Antarctica is concrete. You've got to warm the aggregate, you've got to warm the water, you've got to warm the cement, you've got to mix it together and keep it warm. You've got to put it in the hole that you've had a blower running in for days. Then you've got to put a tent over it, and you've got to guarantee that it stays warm for the curing period, which is probably 2 weeks or something, in that order, because depending on the temperature. And you've got to have the people to do it. It's a massive project. And he said, and if it freezes, you've got a very expensive blob of aggregate again. So it's got to be dug out and you've got to start again. So what we've moved to doing is getting precast concrete blocks made. And we're using those like for the hut that you were showing, the containers, the 20-foot containers. We can buy a 20-foot container. We can have it, well, we could pre-COVID, have it shipped into Tassie, lined with insulation, stainless. This is factory done. So it's a brand new container, insulated, stainless steel lined to Kingston for under 50 grand, which is a really effective way of doing a building. Then we have it on precast blocks, which can go down, and they sit on, the container sits there and it's there forever, and it's got a life of probably 20 or 30 years, not on Macquarie Island, but on the continent. And we pre-wire them, put all the switchboards in, ventilation systems, all the rest of it. It's absolutely fantastic solution for field huts. That's for Macquarie Island, that's a different thing. It needs to be plastic though. But that's working quite well. That's sort of the program, that part of the program. We've got new transceive huts in at each of the stations now. Now we're onto the actual antennas and infrastructure. We've gone, the existing antennas have all been hard-drawn copper, and they've got a finite life. We've gone over to flexible stainless. It's not quite as good a performer, but the maintenance cost is way down.
Okay, thanks, Kim. We'll
done.
Show our appreciation.
Again.
And thank you to all our speakers today. These presentations will become available on Ham Radio DX, so Hayden's YouTube channel. So in due course, so you can watch these again and pick up the things you missed. So thank you to all our presenters, and please our presenters gather over near the very nice wine over there. Thank you very much. Cheers.
Thanks for organising it.